Welcome back, everyone. Lecture 3 is on extremely low-frequency electromagnetic fields. But first, a polling question. Now we are going to shift to extremely low-frequency electromagnetic fields, and the research focuses on occupational exposure, power lines, and especially cancers like childhood leukemia. The critical threshold for childhood leukemia appears to be between 2 and 4 milligauss. Among adults, the critical threshold for cancers is between 10 and 12 milligauss and possibly lower. The key cancers of concern are leukemia, brain tumors, and breast cancer. There are a few studies documenting damage to sperm at 1.6 milligauss and miscarriages at 16 milligauss with exposure of the mother during her first trimester. And then there are symptoms of electrohypersensitivity similar to those we discussed with radiofrequency radiation. Very few scientific studies were published on the health risks associated with power lines prior to 1985. This all changed with a landmark study by Nancy Wertheimer and Ed Leeper in their 1979 paper on childhood cancers and electrical wiring. This study created a surge of interest. However, eventually the interest began to fade as the studies were confirming that exposure to extremely low frequencies was associated with both childhood leukemias and adult cancers in occupational settings. 4 major reviews from 1996 to 2002 are worth mentioning here as they summarize the research done to date. The 4 major reviews during this period were conducted by the National Institute of Environmental Health Sciences, the U.S. National Research Council. I wrote a major review in 2000 published in Environmental Reviews, and the IARC monogram on ELF EMFs where they classified this as a possible human carcinogen. This is a very important document. In 1979, Nancy Wertheimer and Ed Leeper published a paper on childhood cancers associated with something called wiring configuration. Back then, they didn't have portable Gauss meters, so they estimated the magnetic field by the proximity of the power lines and the number and thickness of the hot wires. Dr. David Savitz repeated this study in Denver, Colorado in 1988 and confirmed the results for childhood leukemia, but not for childhood lymphoma or brain tumors. Dr. Sam Milham reported in 2001 that childhood leukemias increased substantially after electrification of a community, and I'll talk more about that in a minute. Here we have a graph of the odds ratio in the magnetic field intensity in milligauss. An odds ratio above 1 implies an increased risk of cancer. An odds ratio below 1 signifies a decreased risk. The Wertheimer and Leeper study was repeated in various countries, and this is where the study falls in this graph. When the magnetic field is plotted against the odds ratio, there appears to be a linear correlation with multiple studies. The higher the magnetic field, the higher the odds ratio. When meta-analyses are done, this is a combination of several studies to increase statistical significance, they show the same trend, although at much lower odds ratio. This is showing a dose-response relationship between the strength of the magnetic field in a home and the risk of child developing leukemia. Milham and Osiander in 2001 took a different approach to determine the role of electricity on childhood leukemia. They examined the historical childhood leukemia rate as the electricity was being rolled out. They did this in both the United Kingdom and the United States, and they reported a 24% increase in childhood leukemia mortality with every 10% increase in percentage of homes serviced by electricity. Here are some of their results. The numbers on the right are the percentage of homes with electricity. The leukemia rate for a 3-year-old increased from 1 per 100,000, with 43% of the homes having electricity, to almost 4 per 100,000 by the time most of the homes had electricity. As the use of electricity increased, so did the rate of childhood leukemia. Studies on childhood cancers and magnetic field exposure indicate the following. Magnetic fields are possibly carcinogenic, according to the International Agency for Research on Cancer. The threshold appears to be between 2 and 4 milligauss for in-home exposure. Other cancers are possible. One study of lymphoma, and there have been 2 studies on brain tumors. Younger children are at greater risk. Nighttime exposure is important. Parent exposure to magnetic fields may be important and may be affecting the offspring. School environments contribute to daily exposure. Guidelines exist. They range between 2 and 3 milligauss in Sweden, but most countries have a guideline of 1,000 milligauss. These guidelines are inadequate to protect public health of either children or adults. The recommended guideline should be less than 1 milligauss for long-time exposure to protect those who are most vulnerable. In science, we do 3 different types of testing. And the more these different tests agree and support one another, the more confidence scientists have in the results. One type of study is the epidemiological study that measures human populations under realistic conditions. This type of research examines the association between an agent and an outcome. An agent may be tobacco, and an outcome may be lung cancer, for example. A second type of study is called the in vivo study with living organisms. This determines a cause-effect relationship. Sometimes humans are used, but often mice, rats, or other species are used for testing. This study measures cause-effect in a controlled laboratory setting. The third type of study is called the in vitro study, meaning in glassware. The focus here is on the reaction of cells and organelles, and the purpose is to understand mechanisms. All of these methods have their strengths and weaknesses. Many of the studies that I'm sharing with you in these lectures are based on epidemiological research, and it's important to know how to interpret the results from these studies that are expressed using the odds ratio. Remember, an epidemiological study measures an association between an agent and an outcome. An odds ratio is a ratio between the number of observed cases and the number of expected cases. When the odds ratio equals 1, there is no difference between controls and cases. When the odds ratio is less than 1, there is a lower risk, and when the odds ratio is greater than 1, there is a greater risk. The statistical significance of that risk is based on the confidence interval, which is often set at 95%. Consequently, scientists base their decisions with a 95% confidence that the results are real and are not due to chance. An odds ratio of 1.5 means a 50% increased risk. An odds ratio of 2 is a 100% increased risk or a 2-fold increased risk. And similarly, an odds ratio of 0.5 means a 50% decreased risk. An odds ratio of 0.8 means a 20% decreased risk. Now, this is a difficult question to answer. However, I'd like you to guess at the answer even if you don't know. Let's take that polling question and examine it in more detail. Remember, the statistical significance is determined by the 95% confidence interval, which implies that 95% of the responses fall within this interval. For the first pair of measurements, we have the same odds ratio of 1.5, but different confidence intervals. The confidence interval that does not extend below the line for 1 is statistically significant. The second pair of values has an odds ratio of 3, and the confidence interval that remains above the line is the one that is statistically significant. So significance is not determined by the odds ratio, but rather by the confidence interval. A very high odds ratio may not necessarily be statistically significant, as you can see here. The same applies for values showing a decreased risk. The odds ratio that is statistically significant has the confidence interval that does not extend above the line in this graph. Why am I spending so much time on this point? Because if you want to interpret data quickly, the odds ratio and the confidence interval are critical. Some people who look at tables go glassy-eyed. They don't know what to do, and they move on to learn how the author interprets his or her results. But it is important to independently review the data to see if you agree with the author. One quick way to find out what is important in a table is to examine the 95% confidence interval. This table lists a number of studies that were done at different magnetic field exposures. They are subdivided in three groups based on the magnetic field. A quick scan of the 95% confidence interval for the first group shows that nothing is statistically significant. A scan of the second group shows the same. A scan of the third group above 0.3 microtesla, which is 3 milligauss, shows 5 results that are statistically significant. The odds ratio for these results range from 1.7 to 4.57, and all are statistically significant. This table is showing what appears to be a threshold value of 3 milligauss for childhood cancer. A very important paper came out in 2008 showing a genetic basis for childhood acute leukemia. For children who lived within 100 meters of transformers or power lines, the interactive odds ratio was 4.31 with a confidence interval of 1.54 to 12.08. This is significant. The interaction in this case is between DNA repair genes and the magnetic field. When the magnetic field is elevated, the DNA repair genes do not function. According to the authors, our results suggest a possible association between electric transformers and power lines and the gene in patients with childhood acute leukemia. What about adult cancers? The 3 most common adult cancers associated with magnetic fields are cancer of the blood, mostly leukemia, cancer of the brain, and breast cancer in both men and women. Acute leukemias in electrical workers in New Zealand appears to be associated with a magnetic field of 10 milligauss. Dr. Anthony Miller, who is one of the speakers at the EMF Medical Conference in January, did a study with electric utility workers in Ontario, and he looked at both the magnetic field and the electric field, and this is what he found. When both the electric and magnetic field were low, the odds ratio was 1.2 and not significant. When the magnetic field was high and the electric field was low, there was an increase in the odds ratio that is statistically significant. And when the electric field was high, the odds ratio was even higher and was significant statistically. The conclusion is that electric fields may also be harmful. Electric utility workers in the US have an increased risk of developing a brain tumor between 10 and 12 milligauss. Several occupational studies have documented increased risk of breast cancer for both men and women. You will notice that most of these studies were published in the 1990s. Currently, 1 in 8 women will develop breast cancer during her lifetime. For men, the risk is 1 in 833. Obviously, more women than men develop breast cancer. If the odds ratio increases to 1.5 and is statistically significant for both men and women, This means thousands of women are at risk, while only a handful of men are at risk of developing breast cancer during their lifetime. Now we are going to shift to in vivo studies and asking the question, does the magnetic field affect breast cancer growth in rats under controlled conditions? These data were reviewed by the National Institute of Environmental Health Sciences in 1998. Their conclusion was that nothing can be said about breast cancer in rats because the experiments were so different. However, sometimes you can find a gold mine in data if you look carefully. Here we have the references cited. Number of animals per experiment. Sometimes a chemical initiator was used to induce breast cancer, but not always. Here we have duration, both in terms of the length of the experiment and the daily exposure. And finally, we have the magnetic field exposure. The data include incidence of cancer, number of tumors, size of tumors, and latency for tumor development. These I ranked as either beneficial or harmful, and this is what the results look like. The solid squares indicate a harmful effect, and the dashed squares indicate a beneficial effect. What this table tells us is that there appears to be a harmful effect at the lower magnetic field exposures, a zone with both harmful and beneficial effects. And at the highest exposure, we have a beneficial effect of magnetic field exposure on the development of breast cancer in rats. This is not what I expected. However, it is possible that at lower magnetic fields, the cancer cells are stimulated, and at higher magnetic fields, the cancer cells are inhibited by the magnetic field, just as they are inhibited by ionizing radiation. The final reference on breast cancer that I would like to share with you is this in vitro study with human breast cancer cells. Using human breast cancer cells rather than cells from other species makes this research highly relevant. This is a very important paper by Liberty, published in 1993 and replicated by at least 2 other labs. Liberty took estrogen receptor positive human breast cancer cells, shown here as red circles, and he exposed them to estrogen, represented by E, which caused the cells to grow. Estrogen is a nutrient for estrogen receptive breast cancer cells. He then exposed the breast cancer cells to a magnetic field at 12 milligauss, which caused the cells to grow. When he exposed the cells to either melatonin or tamoxifen separately, their growth was reduced. What they concluded from this research is that when you expose your cells, these cells, to electromagnetic fields plus melatonin and tamoxifen, neither melatonin nor tamoxifen inhibit the cancer the same degree. For this reason, it's really important for women with estrogen receptor positive breast cancer to avoid magnetic fields. Magnetic fields interfere with the oncostatic action of both melatonin and tamoxifen. Milham in 2009 looked at the historical evidence for common illnesses we have today. I am going to share 2 of these with you, cancer and heart disease. In 1940, approximately 30% of the farms in the US and about 80% of urban centers had electricity. Milham then compared the rural to urban communities within various states that had a high percentage of electrification, as shown here. The numbers represent percent electrification within each state, with RI standing for Rhode Island, CT for Connecticut, etc. In this group, there is little or no difference between rural and urban centers regarding the availability of electricity. And here are the states with a low percent of electrification, between 28 to 57%. Most of this is going to be in urban centers in these states. This graph shows that with an increase of electrification, the cancer rate also increases. This appears to be the case when we compare urban to urban centers, rural to rural centers, and urban to rural centers. According to the authors, there is a 49% urban increase in cancer deaths with increased electrification. Here we have the results for heart disease deaths, and it shows a similar trend for urban versus urban, rural versus rural, and urban versus rural. Now, there may be other reasons for this difference. All we see here is an association between electrification and deaths from heart disease. In addition to cancers, miscarriages have been reported when the mother has prenatal exposure to magnetic fields. Here we have 3 statistically significant risk ratios. For exposure above 16 milligauss, the risk ratio is 2.9. For early miscarriages, 5.7. For susceptible women who have previously miscarried, 4.0. Magnetic field exposure at or above 16 milligauss increases the risk of miscarriage. Sperm seems to be very sensitive, as levels of 1.6 adversely affects sperm quality. There is some limited evidence for neurological disorders with EMF exposure. Residents near power lines and mortality from neurodegenerative diseases in Swiss population. In this study, they reported an increased risk of Alzheimer's and senile dementia for people living within 50 meters of a high voltage transmission line for 10 and 15 years. They found no relationship with ALS, Parkinson's, or multiple sclerosis. Women exposed during pregnancy to magnetic fields have a higher risk of asthma developing in their offspring. This graph shows percentages of offspring remaining asthma-free. The higher the magnetic field, the more asthmatic offsprings. Authors conclude that our findings provide a new epidemiological evidence that high maternal magnetic field levels in pregnancy may increase the risk of asthma in offspring. Our exposure to extremely low-frequency electromagnetic fields in our home comes from 3 types of sources: external wiring, internal wiring, and electric appliances. External sources of electromagnetic fields comes from generation, transmission, and distribution of electricity. The photograph on the right shows fluorescent light bulbs glowing under a high voltage transmission line. This is due to the high electric field. We are going to take a quick tour of how electric power is distributed. We start with power generation. This shows a 3-phase, 3 wires at a voltage of 13.8 kilovolts. This goes through a step-up transformer whose job is to increase the voltage on the transmission line. The higher the voltage, the less power lost with long-distance transmission. Here we have a 230 kilovolt transmission line. The electricity flows through a substation that has step-down transformers that reduce the voltage before it goes to lower voltage transmission lines, and eventually to primary and secondary distribution lines. Several additional step-down transformers further reduce the voltage in the distribution system until it reaches the appropriate value depending on the customer. What is important to note is that the electric field is a function of voltage, and the magnetic field is a function of current. Now for a polling question. You may wonder why this information is important. It's important to know the temporal and spatial variations in exposure. This will determine when a measurement should be done, where a measurement should be done, and whether more than one measurement needs to be done. The electromagnetic field consists of 2 components, an electric field and a magnetic field. Here we have 3 power lines that differ according to their voltage from 500 kilovolts to 115 kilovolt lines. Transmission lines have a greater voltage than distribution lines. As we move away from the power line, the distances are shown in red. The electric field decreases exponentially with distance. Ideally, the electric field should not exceed 5 volts per meter. And as you can see here, at the edge of the right-of-way, the electric fields are much higher, and they increase with line voltage. Here we have the same 3 transmission lines as in the previous slide, but this time we are looking at the magnetic field. Distances are shown in red. Instead of one value, we now have 2 values for magnetic field. One is based on the average load, or the average current, and the other is based on peak load, or peak current. The magnetic field, like the electric field, decreases exponentially with distance. Ideally, the magnetic field should not exceed 2 milligauss for constant exposure. And as you can see here at the edge of the right-of-way, the magnetic fields are much higher than 2 milligauss. Voltage is electrical pressure, and one way to think of this is using water as an analogy. A 200 kilovolt transmission line is like a fire hose under high pressure. A 2.3 kilovolt distribution line is like a garden hose. And a 500 volt distribution line is more like a straw. When 2 objects have the same electrical potential, there is no pressure and no current flow. This is called equipotential. This would equate to a tube of water that is level. There is no water flow, no electron flow, and hence no current. At different electrical potentials, we have a moving electrons and we have moving water. Voltage is measured in volts, current is measured in amps, moving electrons produce a current, and current can kill. According to Ohm's law, there's a relationship between voltage and current and resistance. The magnetic field here is represented by circles around a conductor or wire. The electric field is represented by red lines in the slide. The electric field can easily be shielded by objects like trees and buildings. Magnetic fields are difficult to shield and penetrate most objects. The reason the magnetic field is represented by circles is because iron filings form a circle around a charged wire, as shown in the bottom left image. And the right-hand rule shows you which way the current is flowing, your thumb, and the magnetic field wraps around the wire, your fingers. External sources of electromagnetic fields include power lines, transformers, wire from the service drop to your home, and underground wires or plumbing. Internal wiring can be a significant source of a magnetic field. High values will be found at the service drop and the electrical panel. Knob and tube wiring, common before 1940s, produces a large magnetic field in a room and needs to be replaced and updated. The magnetic field from a fuse box on the other side of the wall penetrates a wall, so it's very important to make sure that you are not sleeping close to the fuse box. And if there are unequal return currents, they will create a magnetic field. The third source of electromagnetic fields are electrical appliances. The most important room in the bedroom is the bedroom, where the magnetic field at night should be less than 2 milligauss and possibly lower. The U.S. Environmental Protection Agency published a document in 1992 of the magnetic fields emitted by various appliances. 2 appliances we may use in the home are electric shavers and hair dryers. Some give off a very high magnetic field, but they are only used a few minutes daily. Those who work with this technology have much higher cumulative exposure, like hairstylists. In an office environment, air cleaners, copy machines, fluorescent lights, and electric pencil sharpeners can generate a very high magnetic field. so it's important to stay away from these appliances when they are being used. Now for a polling question. Magnetic field exposures vary throughout a normal workday depending on what a person is doing. Here we see that the sewing machine operator is exposed to the highest magnetic fields, followed by the office worker. The red line represents the mean magnetic field during the workday. The red band is for magnetic fields between 2 and 10 milligauss that have been associated with both adult and childhood leukemia. One of the best reports on the biological effects of electromagnetic fields was produced by the Bonneville Power Authority in 1996. I'm going to share with you the results from this report on EMFs in human cancer studies. They classified the studies according to residential exposure, occupational exposure of adults, effects on children whose parents were occupationally exposed to electromagnetic fields, and studies on appliances. For residential exposure near power lines, they reviewed 19 studies on the effects on students and found that 11 studies reported an increased risk of leukemia and no study reported a decreased risk. For adults living near power lines, of the 11 studies, 4 reported an increased risk and none reported a decreased risk. Here are the results for occupational exposure. The 3 most common cancers reported were breast, brain, and blood. Disturbingly, children who are born to parents exposed to electromagnetic fields may have an increased risk of developing cancer. Of the 212 studies, 48% reported an increased risk, 48% reported no effect, and 4% reported a decreased risk. One tool used in risk assessment is called weight of evidence. And now for a polling question. This is the way Health Canada assesses weight of evidence. And this is how weight of evidence should be assessed. A study showing no effect has no weight. People don't like to live near power lines and would prefer they be buried, but burying a power line is more expensive, so this is not something the utility wants to do. Is there an advantage to burying power lines? We can compare overhead versus buried power lines based on 8 criteria: the electric field, the magnetic field, the corona effect. This refers to an electric discharge that you can hear when you approach some transmission lines. It's a buzzing sound. This produces ozone and nitric oxide. It damages evergreen trees, and it produces dirty electricity. Contact current, ground current. Overhead lines can act as an antenna for microwave radiation, but not buried lines. A safe distance can be much closer with a buried line. And there might be health effects if the magnetic field from the buried line is above 3 milligauss. Here we see the guidelines and effects of electromagnetic fields. Once again, the guidelines vary orders of magnitude in different jurisdictions, and some of the best guidelines are in Europe. In the Netherlands, new buildings near transmission lines must have a magnetic field less than 4 milligauss, and in Israel, you can't sell your home unless the magnetic field is less than 10 milligauss, which is still too high. The effects are shown in red, and you can see that most of the guidelines do not protect against these health effects. Here are some recommendations for how to deal with electromagnetic fields in your home. External wiring. Distance is important. Move your bed away from wires. If the power line is at the front of your home, try to move the bedroom to the back of your home. Resist utility upgrades that move wires or transformers closer or that increase the current. Ask the electric utility about underground wires and pipes. Here are some of the recommendations to deal with electromagnetic fields in your home from internal wiring. Make sure that you spend little time near the service drop or the electric panel. If you have knob and tube wiring, ask an electrician to replace it. Ask the electrician to measure the current on your plumbing to see if there is a ground current problem. And purchase a meter and measure hotspots in your house periodically, especially in the bedroom. And finally, you should minimize your use of some of the high magnetic field appliances. You should maximize your distance from the appliances when you're using them as much as possible. And the bedroom is critical. Unplug the electric blanket and move the alarm clock away from your bed. And here are the two final polling questions for this lecture. We'll take a short break.